imagine a spinning disk rotating clockwise. The disk doesn't move through space, but it's spinning. So we might want to describe the distance or the displacement through which it spins. That's called rotational or angular displacement. And we use the symbol theta, and we can measure that displacement, how far it spins, how much it spins, in rotations, degrees, or radians. And the conversion, of course, is 1 rotation equals 360 degrees equals 2 pi radians. Just briefly reviewing, a radian is 1 radian is the angle where the arc length, that's the arc length here, is equal to the radius of the circle. So the definition of the angle in radians is found by the ratio of the arc length, which we call S, to the radius of the circle. And when we have 1 radian, just to get a sense, if you look at it, you can see it's about 60 degrees. But since the circumference of the circle, we can find the 2 pi. So let's take 1 rotation equals the arc length. The arc length of 1 rotation is the circumference of the circle. That's 2 pi r. And we divide that by the radius. And we get 1 rotation. This, where we get 1 rotation, is 2 pi radians, or 6.28 radians. What that means for our rotating disk or our circle above is that if we take the radius and we wrap it around the circle, we go 1, 2, 3, 4, 5, didn't do this very well, 6. There's a little bit of gap there between the complete circle, which would be 6.28 radians, and the 6 radiuses that I wrapped around. So, just out of curiosity, what is 1 radian? Well, we can use our conversion factors that I've written up there. 1 radian, I want to change radians to degrees. So 360 degrees divided by 2 pi radians. 360 degrees is equal to 2 pi radians. That's our conversion factor. I write it that way. The radians will cancel, and I'll end up with an answer in degrees. This ends up being approximately, putting that into the calculator, 57.3 degrees. Okay, so we now want to talk about the rate at which the wheel is spinning. That will be our angular velocity, or rotational velocity. and traditionally we use this Greek letter lowercase omega, and we define first the average velocity. Remember, we did this back in week 2 for regular velocity. The average velocity will be the change in angular displacement over the change in time. That gives us the average. But if we want the instantaneous, you remember what we did. We must take a very small interval in the limit that delta t approaches 0 of the delta theta delta t. This, of course, is equal to d theta. I'm going off the screen, dt, the derivative of theta with respect to t. So our disk is spinning, and if the velocity is constant, then the average and the instantaneous will be equal. But if we take the disk starting from rest and have its speed increase, then, or if we take a spinning disk and have it slow down, then we want to be able to measure or describe its angular acceleration. And for that, the symbol is alpha, and the average alpha will be, no surprise, the rate at which the angular velocity changes. And that gives us the average. And if the acceleration is constant, then the average and the instantaneous will be equal. But in some cases, the acceleration may vary. And then we need to talk about an instantaneous acceleration. And that's going to be equal to, again, the same routine, no surprise, the limit as delta t goes to 0 of delta omega delta t. We have to take that ratio over a smaller and smaller limit, and you can recognize that as d omega dt in terms of calculus notation. So now we have all three quantities, displacement, velocity, and acceleration, defined. And if the acceleration is constant, then similar to what we did talking about kinematics earlier, we can generate 4 kinematics equations for the case of constant acceleration. And just taking the definition of acceleration, our delta omega here, that's omega final minus omega initial. So we rewrite it and we get equation 1. Omega final equals omega initial plus the angular acceleration times the time. And similarly, for constant acceleration, we get that the average velocity, that the displacement, the total displacement in any situation, is going to be the average angular speed times the time. And the average angular speed for constant acceleration is omega final plus omega initial over 2 all times delta t. Combining these two and doing some algebra, which I won't show here, we can generate the other 2 equations that parallel what we know from week 2, week 3, and that's that the total angular displacement will be equal to the initial velocity times the time plus 1/2 the angular acceleration times the time squared. And the final equation is that the final omega, the final angular velocity squared, equals the initial angular velocity squared plus 2 times the angular acceleration times the angular displacement. If you go back and look at your 4 kinematics equations from our previous study of kinematics, you'll see they parallel these exactly.